Good afternoon, dear participants. I welcome you after this lunch session, and we are going for our session on EDA tools, electronic design automation tools, and we also call them as CAD tools, computer design tools. So before start of any design, we should know means what are the tools available with the designer. This is a very important input with the designer, and if you have proper knowledge about the CAD tools, then you can easily proceed with your work. So important tools with the designer are CAD tools and the input design. Circuit design means whatever form is there for your circuit, depending upon them you have to choose the appropriate tool for design of your circuit. So outline of this session are, first of all, we are going to just brief about the design flow. Then we will discuss design different type of tools. Basically, we can divide CAD tools or EDA tools in 3 different categories, and these are synthesis tools, capture tools, and simulation tools. And we are going to discuss all these tools in detail. After that, we are going to conclude this session and then references for this whole session. First of all, if we just look into the design flow of VLSI, then we can just start our design entry by using either some HDL, that is hardware description language, or it can be under HDL there are 2 different languages, VHDL or Verilog, and depending upon the designer knowledge and designer comfort, they can opt out of these 2 programming languages. They can go for VHDL or they can go for Verilog. So we can enter our design by using this VHDL or Verilog, and this type of design entry is known as textual entry of design. Once you have entered this program code, then next thing is this code is converted into RTL, register transfer level, where your code will be converted into number of registers along with its netlist connection. Then next part is, now you can see that the partitioning of design, because at the same time whole design cannot be active at present. So we can partition our design depending upon its functionality. If some part of our design is functioning first and a result of that design is required by the other part, so we partition our design in such a way that whenever functioning of first part is required, it will be processed first, then its result will be used by the second part, that is part B. And if another partitioning is there, C, and if the result of partitioning B is required by C, then it can be taken in this manner. So after your this RTL, design is partitioned and your circuit is partitioned in a manner, sequential manner, you can say. Once this partitioning is done, then next step is floor planning. Whenever we go for design on any platform, let us say we are designing our circuit on FPGAs, or if we are designing our circuits on ASICs, where ASIC stands for application specific integrated circuits. So first thing is we have to select the floor out of the available different floors. Once that floor is selected, then we have to select next part. We have to select particular portion of that floor where your circuit is going to be placed. So before placement, floor planning is very important, and once this floor is decided, then we can place our circuit at specific portion on that particular floor. So once our circuit is placed on the floor, the next step is now you have to route the circuit. So that routing of circuit is done basically to complete the netlist. Means whatever connections are there in your circuit, you have to route all the connections of your circuit, and once these connections are done, then your circuit is complete. So this is the complete design flow, and for this basically complete design flow, you have different tools available in the market. You have different CAD tools, and you should have good knowledge about those tools. Means wherever you want to work, first of all you should have that tool in your hand. Only then you can proceed for your design entry. Now, as we told that there are three categories of your EDA tools. First category is design synthesis tools. Second is your design capture tools. Then verification tools. First of all, we are going to discuss design synthesis tools. Under these design synthesis tools, these are further divided in subcategories like behavioral synthesis, RTL synthesis, then logic optimization, then structural to layout synthesis that include your placement and routing, and then layout synthesis. So first of all, we are going to discuss this behavioral synthesis. Actually, behavioral synthesis, it provides the best and fastest simulation. It is best to debug the operation of the complete system. It is used to decide upon and assign resources based on area and timing requirements. And behavioral synthesis, it is used to insert registers for the purpose of pipelining, so that you can enhance the speed of your circuit. This is basically for the purpose of your speed enhancement. So one example of this behavioral synthesis is when you design your circuit using ISC environment, Xilinx ISC environment, and integrated software environment. We enter our design using either VHDL or Verilog. So once our design is entered using this VHDL and Verilog, then we simulate this design. We check the behavior of our circuit, and that behavior of the circuit can be simulated with the help of some simulator. And ISC has its inbuilt simulator in it, that is iSim. And apart from this ISC simulator, another simulator is Model Sim, that is also available in the market. So if you want to work in these areas, in basically ISC is used for front-end VLSI design, and this ISC software is used for programming of your FPGAs. If you don't have this software with you, you can easily download the educational version of this software from Xilinx site, and you can start your designing with the help of this software. So it is available on the site. So once your circuit is edited using VHDL or Verilog, then we simulate its behavior. So here you can see that this is the behavioral simulation, and we are using here one simple gate with 2 inputs and 1 output. So here you can see that this gate is, so from these 2 inputs you can say that one name of this input is X. X is high, where this blue line is there, it is high here, and then Y is also high, and your output Z is low. Means when input X and Y, these two are 1 and 1, then your output Z is 0. It means that this one is for your XOR gate. So here XOR gate is designed and it is simulated, and its behavior has been checked with the help of ISC simulator. Next is RTL synthesis. Basically RTL synthesis, it takes the RTL description. It takes the RTL description in the form of HDL. It can be VHDL or Verilog. Then it converts this RTL description or RTL language into a set of registers and its combinational logic. Mostly these RTL descriptions are captured by hardware descriptive language, and these are your VHDL and VLSI, VHDL and Verilog. In your program, you can use different control flow instructions like if, then, else. Case statements can be there. You can use number of iteration in your program while you edit your program, and your program can have hierarchy. Hierarchy means you can have your program, then you can have sub program, and then subroutines may be there. So you can follow some hierarchy in your program. Then you have to assign some bits with your inputs, outputs. So you have the option, you can use different number of bits for your input data, and you can use different number of bits for your output data. So it is the option of designer whether you want to go for 16-bit input or 16-bit output. You can go for 8-bit input, 8-bit output, depending upon the application. You can change this word width, and you can go for the bit selection, number of bits. And another thing is, while you write your code, it can be either sequential or it can be parallel. Sequential means you can process your data one by one in sequential manner, or you can process your complete data in just one clock, and that is known as your parallel operation. Then we can specify registers wherever those registers are required to store some data that is required by some other section, like just like in our partitioning. If partition B is dependent upon partition A, then we can use one register there that will act as pipeline, and then whatever result of partition A will come, that will be stored in your register, and whenever it is required by partition B, then partition B is going to take that data from that pipeline register, and it is going to process that whole section. So RTL compiler is basically it is used to convert RTL description language into sets of registers and combinational logics. Means it takes input as a program, and that program may be your VHDL or Verilog, and then your RTL synthesis. So this is one example. Again, this is the example of your ISC simulator. Here you can see that we have one example of half adder. We are basically controlling two outputs, sum and carry, and this is the complete code. This is the complete code of your design, and this is you can say RTL description in textual form. We are writing a code that is required, half adder code, and we are writing that code in VHDL language. Now this RTL description will be taken by the next section, that is RTL synthesis section, and it will convert that section into its equivalent, you can say a register level. Means one block will be created, and here you can see that X and Y two inputs are there, and this is the basically block for you can say half adder, and we have two outputs, sum and carry. So your basically that VHDL code that has been converted into this block with its inputs and outputs. You don't know about the internal architecture of this thing. So this thing is, next thing is logic optimization. So it takes the logic description from RTL synthesis. Whatever block you have generated in RTL synthesis, you basically take that block, you strip out, software strip out the registers from that block, and then further optimize the network of gates that are required to implement the specific function. So in this section we optimize that block once again, and we remove the registers, and then we optimize the complete circuit. Once the optimization is done, then again these registers are reunited, and the logic is basically optimized logic is available for the next section. So the type of optimizations normally done in this section are two types of there. First is your technology independent logic optimization, and second one is your technology dependent optimization. Under technology independent logic optimization, it takes care of you can say general rules like different Karnoff maps is there, your Maklinsky method is there. Then it also takes different theorems. It takes Boolean algebra, different theorems, De Morgan theorem. Means whatever is you can say standard rules are there, and using these standard rules we optimize our circuit under this first category, that is technology independent logic optimization. So we take care of all the rules, we take care of all the theorems, and we use our tabular method, that is Maklinsky method, for optimization of our design. Once this part is done, then another kind of optimization takes place that is known as your technology dependent logic optimization. Technology dependent optimization, basically it varies from one vendor to another vendor. So many vendors are available in the market for your CAD tools. They are providing very good solutions. They are providing very good EDA tools. Some of the vendors are like your Virtuoso by Cadence. Then you have Synopsys. Then Mentor Graphic is there. Microwind is there. Tanner tools are there. So many different you can say vendors are there, and they are providing some good tools for design of your circuits. So this section, that is your technology dependent or logic optimization. Under this section, basically it varies from one vendor to another. So technology dependent or logic optimization, number of libraries are there, number of components are present in those libraries, and you have number of options so that you can choose best options available in the library of your software, and you are going to come up with one circuit that will be optimal in all sense. We can say it will be optimal in your speed, it will be optimal in your power consumption, it will be optimal in your you can say area consumption. So these two different optimization takes place under this logic optimization part. And here you can see that it takes the this block. It when you click this one, you will get this section, and this section. So you will get deeper inside the circuit, and this circuit is logically optimized. And two type of optimizations will be performed. One is your technology independent, another one is your technology dependent. Then once this thing is done, then next thing is structural to layout synthesis. Up to this part, up to this logic optimization part, if we are dealing with our FPGA programming, then straight away we can download this or we can map this circuit on our FPGA. So if basically we are dealing with backend VLSI design, then we have to convert layout from this structural output, you can say. So this part is basically your structural to layout synthesis. Once a network of logic gates and registers is available with you, then these logic gates and registers can be automatically converted into a layout. So that layout can be used to design your own IC. And for creating this layout, two main phases are there. One is your placement. You have to place your circuit on silicon, and then you have to route it. And this part is basically when you are dealing with your backend VLSI design, when you are designing your own chip in the form of ASIC. And if we are dealing with FPGA programming, then this placement will be on the already available resources on our FPGA. We have to place our circuit on those FPGA resources, and then we have to route those resources, and we have to come up with the final product in case of FPGAs. So this placement basically it is the task of placing the modules adjacent to each other in order to reduce the area. Whenever we go for placement, our first aim is our placement should be in such a way that we can place our circuit on very less area, because area is very important factor in VLSI design. If we can reduce the size of our circuit, then we can make our product cost effective. Then for this placement, normally we use two type of placement algorithms are there. One is your min-cut algorithm. Min-cut algorithm means if two partitions are there, and two partitions A and B are there, and we have to place our circuit in these two partitions in such a way that minimum number of cuts will be there between two partitions, means less number of cut lines between will be there between these two partitions. Next is your thermal annealing algorithm. It is used to check the temperature, and whenever you place your circuit, it check the temperature, how much temperature is achieved with the help of this kind of placement, and whether it is meeting the requirement of our design or not. If it is not meeting our requirement, then we have to change the placement and so on. Once our temperature reaches the required limit, then we freeze that placement. So for placement, these two most commonly used algorithms are used. One is your min cut algorithm, and second one is your thermal annealing. And then once your placement is done, and next thing is routing. Routing is basically, it takes place between modules, and it is done according to the netlist generated by the RTL. So you have one netlist, and you have to make those connections between different components based on that netlist. Different type of routers can be there. Example of those routers, one is your channel router, and channel router, it can route your rectangular channels. Then switch box routers are there. They can route more complex channel shapes than your channel router, means they can provide complex routing as compared to channel routers. And then maze routers are also there. They can route just any kind of configuration, but they are comparatively long running times. You can say that the maze routers are complex in nature, but they provide optimal solution, and also they are time consuming. They take more time to route your circuit. Apart from these routers, other routers are also there, and one of those category is global router. And global routers are special kind of routers. Those routers works during the placement algorithm, and they plan where routes will travel whenever layout is finally placed. So global router, basically it gives you information about all the possible routing. And just like these global routers, we also have global placements. So before we place our circuit, our software determine what are the different options of placement. Means it will check all the options of placements, and that is basically your global placement. And then our software, it checks which one is best suited for our design. That will come under the category of your detailed placement. Likewise, we have global routing also. Global routing also, it gives you information about all the paths, all the paths available with you, and finally it is going to select the one path that will be optimal in all sense, and that particular path will be freezed, and it will be called as your detailed routing. So both placement and routing, they have global as well as detailed part. So we can also say that this placement and routing, this is not, you can say, uh, it goes simultaneously. Means whenever we place, we also route the circuit. Means we place and then we check the routing. Again we place, we check the routing. Means these are simultaneous. It is not like that we are going to place alone and then we are going to route. First of all, we place, then we route, we check the optimality in sense of your speed, in sense of power consumption, in sense of your area consumption. So these are basically two steps which normally we perform simultaneously, and we try to find out the best placement and routing for our complete design. Then as we have already discussed in our plan, design flow. So once your partitioning is done, then next part is your floor planning. Floor planning means basically here, it is the exercise of arranging blocks of layout within a chip to minimize area and maximize speed. So it can be on silicon area, or it can be on already available resources in case of FPGAs. So floor plan editors provide graphical feedback about the size and place of modules. It gives you information about the size of your circuit, where your circuit is placed, and it also gives you information about the connection of your different IOs. And in this case, you don't have information about the internal layout of your circuit. So you will get the size and you will get the interconnections state. So in addition to these editors, in addition, these editors also show connectivity information between modules, and that connectivity information will be in the form of rats nets, means state wires, and those wires are not routed wires. Those wires give you information about the connection of your different IOs with your circuit, and those are not completely routed. And these rat nests will be in the form of your straight lines. These are not final routed tracks. So here you can see that we are just giving one example of this FPGA here. You can see that this is the complete FPGA, and in this FPGA, earlier we have shown you XOR gate, simulation of that XOR gate, and then I've shown you two programs. One is your half subtractor. So here you can see that that half subtractor is placed on this FPGA, and in this FPGA you can see that these are different floors, and these floors basically available with the designer. So your software can place your circuit on any one of these floors, but software has to check the optimal floor where your design will be optimally placed. So out of these number of floors, you have to select one floor, and normally this selection depends upon the IOs used in your design. So normally software selects the floor that is closer to the IOs. Here you can see that this is one block of IOs. Two pins are used here, two pins are used here. So for this one, this particular particular floor is selected, and once this floor is selected, then out of this floor, which part of that particular floor will be used to place your circuit, that is selected, so that you get your placement and routing optimal. So out in this floor, this particular part is used for your placement, and once this placement is done, then next part is your routing. So here you can see that this is the routing part, and these are different paths. So earlier in that case, you are just having the information about rat's nest, means you have information about different connections. Those connections are in the form of straight lines, but here these are your different routed tracks, means your final, you can say, detailed routing, this one, and then this is the part where your circuit is routed. So in this manner, once your logic optimization is done, then next part is your floor planning, and once this floor planning is decided, depending upon the inputs and outputs selected by the user, then that circuit will be placed, and once circuit is placed, then it will be routed based on different routing algorithms. Everything basically it runs behind the software, but you should have knowledge about the different you can say operations which are going behind the screen, behind your screen. So once this thing is actually this was FPGA part. Now if we are dealing with our chip designing, then we have to create one layout. Layout means we have to create different layer of mask, and those layer of mask will be used for your complete chip designing. And the layout of regular structures used in your design, such as your RAMs, ROMs, PLAs, registers, files, multipliers, general data paths, and they may be synthesized by software generators. These programs take a number of parameters as input and automatically create a physical layout from them. So different steps are there, and those steps vary from one vendor to another. And some softwares, they are capable of producing actual mask layouts, and those actual mask layouts can be straightaway used by the CAM operation, computer aided manufacturing, where you can make your own, you can create your own chip. And some softwares, they create symbolic layouts in the form of schematic. That schematic maybe it can be your in the form of gates, logic gates, or it can be in the form of these transistors. And this is your mask layout. These are the different layer of mask, and by using these masks we can create different regions on our silicon, and then we can convert that you can say part of our silicon part into IC. So this is whole about your design, and the next part is your design capture tools. Now design capture tools can be you can have three categories of design capture tools, and these three categories are: first one is your HDL design, second is your schematic design, third is your layout design. So whenever we go for any design input, we have to first of all choose means whether we are going to input our design by using HDL language or Verilog language, or whether we are going to input our design by using schematic. That schematic can be in the form of transistor, or it can be in the form of logic gates, or straight away we want to create layout design. So these three parameters also depends upon the circuit available with the designer. For example, if you are working on some circuit, and that circuit you have taken from some IEEE paper, and if that circuit is in the form of transistors, then you should have a software that can take your design in the form of schematic diagram or in the form of transistors, right? And if your circuit available with the designer is in it is in the form of text, it is in the form of, you can say, VHDL language, or it is in the form of Verilog language, then your software, it should be able to provide option of inputting that circuit in the form of these HDL design. So the behavior of your structure of a system may be captured in the hardware descriptive language. Two languages are there, VHDL and Verilog, and it depends upon the designer. If you are comfortable with VHDL design, then you can go ahead with your VHDL, and if you are comfortable with Verilog, you can input your design with Verilog. So this is the option. This is one code you can use. You can write your code either in VHDL and Verilog, and if your software supports this kind of capture or input, then you can go ahead with your this kind of capturing tool. Then next input capture method is your schematic design, and in this schematic design you can input your design in the form of schematic, and your design will be interactive, and it can be input with the help of schematic editor, and interactive editors are available in the market. So if we compare these two, basically design options, or you can say capture options, if we discuss this schematic schematic diagrams are you can say they are easy to understand. You can easily understand these schematic diagrams, and if we just compare it with HDL, is in the form of text, and they are easy to modify, we can say that. So both these capture options have different advantages and disadvantages. So schematic, that can be easily understand, but its modification is difficult, and HDL, it is its modification you can say is easy, but it is very difficult to understand that. So schematic editors are basically menu based. You can have graphical editors, you can create, select and delete parts depending upon, actually it also depends upon the you can say yes, vendor, what kind of facilities they provide you to capture the data. Changing the graphic view by panning, zooming, and these type of options will be there in the software. In ISC environment also you have both the options. Either you can input your design using schematic, or you can input your design using HDL. So likewise this is the one example of your schematic. Either we can input our design using these gates, or we can input our design using these transistors. Then layout also can be captured via code, and it can be captured via interactive graphics. So whenever we are talking about this layout means we are talking about backend VLSI design. We are talking about this ASIC design. So here you can see that in case of ISE environment, you can easily go ahead with your VHDL and Verilog environment. You can program your circuit using this. But whenever we talk about backend VLSI design, backend VLSI design also have means design entry and design capture. It varies from one vendor to another. I'm just here giving you one example of microwind software. You will get exposure of this software also in our coming sessions, and that session is basically on Wednesday. And a person from advanced technology, he is going to give more exposure about the microwind software. But from here time at this point of time, I would just like to explain you what are the three different major steps in your microwind software, how to capture your data in microwind software. First is you can this is the microwind software. First, you have to design your circuit using schematic, and this design can be done by using one software that is known as VHDL. Then once this schematic is ready, then you can convert this schematic into its equivalent Verilog file. You can convert it into Verilog file, and this file is also known as it gives you detailed information about the complete circuit, and we also sometimes call this file as Z file and spice file. So this part is also done with the help of the DSH software. Once this Verilog file is generated, then next part is we move to microwind software, and in microwind software we call, or we can compile this V file, Verilog file, using microwind software. And after compiling this file, your microwind software, it gives you the layout. It generates the layout for you, and that layout will be it will consist of different number of layers, complete layers for designing of your complete circuit. So if you just look into this one, we have three options, three capture options. So if you have your design in the form of, for example, if you are working on some design and that design is in the form of either it is based on transistors or it is based on logic gates, then you are going to start with this schematic part. You will take that circuit input. You are going to design that circuit using this schematic, and then after this DSPH is complete, then you will move for this option. If your design is in the form of this schematic. If your design is in the form of code, or it is in the form of Verilog, then straight away you can start with this step of your Verilog file. So one important thing is this, whatever file you have, let us say you have some code with you, and you want to start from there, then you are going to work in this part, Verilog file, but this Verilog file should be compatible with your software in which you are working, because compatibility is very important in this case. Normal Verilog files you can't use for each and every software. So each and every software, they generate their own compatible files. They normally generate their files in the form of Verilog. And these days, different software vendors, they are also providing these forms, files in the form of VHDL. So means every file is not compatible with each and every software, but each and every software, they provide their own compatible file, and we can use that file straight away. So second thing, either you can go with schematic part if your circuit is in the form of transistors and gates, or you can start with Verilog file if your circuit is in the form of HDL language in the form of text. Or third form is uh, if these two things are there, then you are going to state this, compile your file, and you will get your layout in microwave. If you don't have these things and you want to create your own layout, then you can straight away you can create your own layout. You can straight away work in microwave. You will work in microwave. You are going to create your different, you can say, regions. You can create your PMOS, NMOS, everything you can create in microwave. And but for that thing, you should have a good knowledge of your lambda rules. And once it is known to you, then you can straight away go to the layout design in microwave. So these are different options, and designer can choose any one out of these options, and it also depends upon the availability of circuit, in which form the circuit is available with the designer. So here we can see that what is this layout editor? Layout editor is basically here you can see now. I think it will be easy to understand this concept now. Layout, it can be captured via code in case of generator. So your layout, this layout can be captured via this code also. If this code is there, you can compile it, and your software is going to generate layout for you. And otherwise, layout editors like schematic editors are based on drawing editors. This layout can be also generated with the help of this schematic if your design is in the form of schematic. And then a layout editor might interface to design a check rule. You can create, you can straight away you can work in your this layout part, but for that you should have good knowledge of your lambda rules, and you have to check the design rules in case of this layout editor. And this DRC check, design rule check, it takes care of all the lambda rules, and it creates, if any error is there, you will be notified about that error. So you have different options, and layout can be generated by any one of these options. So these so this is the one example of microwave software. Here you can see that this is the complete layout. You have number of layers present for your design, and here you can see that A, B, this is your carry in, different layers are there, different layer for your PMOS, different layer for your NMOS, then metallization, blue color is showing you the metallization, red color is for your gate, polysilicon. So different layers will be generated. This is basically automatic generation of your complete design, and this thing can be designed on your own, or it can be developed on your own if you are going to work in the layout part straight away. So this is about this layout editor, and the third part is your design verification tools. Now under these design verification tools, you have different options. First of all, we capture the design, and that capturing of design can be with the help of either HDL language, it can be with the help of schematic. And once your design is captured, then we synthesize it, and that synthesis is basically your logic synthesis, and we convert your design, that HDL, into RTL, and that RTL is optimized by using technology independent and technology dependent optimizations. And then it is further it is floor planned, placed, and routed on the area. Either it can be on FPGA or it can be on your silicon area. So once all these things are done, the next part is you have to verify the tools. You have to verify your design. So for that purpose, we have different design verification tools, and design verification tools have different categories, and these tools can be used for the purpose of simulation. These can be used for timing verifiers. Another very important category is network isomorphism, and then layout extraction is there, design rule verification is there, and pattern generation is there. So here, first of all, we are going to discuss this simulation, and this simulation is basically based on your three types of simulations are there. One is your circuit level simulation, second one is your timing level simulation, and third one is your logic level simulation. If we talk about this circuit level simulation is the most detailed and accurate technique where simulator operate on circuit level. An example of these type of simulation is, or you can say example of these type of circuit analysis is your SPICE program. SPICE here stands for your simulation program for integrated circuit environment, and it was developed at University of California at Berkeley. And another circuit analysis program was developed by IBM, that is ASTAP, and commercial version of SPICE is that is available these days, that is your SPICE. So basically this SPICE simulation, it basically works on solution of metric equation, and it gives you based on circuit voltage, currents, and resistances. These type of simulation are highly accurate, but they take long simulation times. So different simulation levels are there. When we go for SPICE simulation, again in SPICE simulation we have different type of levels of simulation. And these simulation levels are also they can vary from one vendor to another. So these simulation levels are your level 1 simulation, second is your level 2 simulation, level 3, and these two are basically combined, and we call them as level 3 simulation, and fourth one is the Sim 4 simulation. So when we talk about this SPICE simulation, we have these three different levels of simulation. Level 1 simulation is the you can say simple one, and in this kind of simulation we take very less number of parameters for simulation. So it is not very accurate. It takes less number of simulation parameters, but yes, it provides us high speed. Your circuit can be simulated in very less time. Second, level 2 simulation, it is basically advanced version of your level 1. Here in this case, more number of parameters are added to consider the simulation, and your simulation will be performed by taking more number of transistor parameters, and it is more accurate as compared to your level 1, but on the other hand it is also time consuming than level 1. And level 3 is basically it is just addition of smoothing parameters into level 2. So that is why this level 2 and level 3 are combined together and known as level 3 simulation. Basically level 3 simulation, it provides smoothing effect in level 2. And the last one is B Sim 4, that is the most accurate, and it consider more number of parameters for your simulation, and it gives you exact accurate results, but the time of execution for this type of this simulation is more. So when we talk about these different vendors, their software, vary based on these different type of simulations, level of simulations. Some softwares they consider less number of parameters. Some softwares they consider more number of parameters for simulation, and some so that is why their cost also vary. So costly softwares they consider more number of parameters for simulation and analysis. That is why the chips developed by those softwares, those are basically used in the market. Those are available in the market for use. So those type of softwares are very you can say accurate, and ICs developed by those softwares they are used in the market, and that is why the cost of those softwares is very high. Some softwares may use 150 parameters for analysis, and then some software may use 70 to 80 parameters for this simulation, and some software may use 30 to 35. So software which is using more number of parameters for simulation purpose for analysis, they are more reliable, and they are basically you can say provide market industry standard tools, and their developed ICs are available in the market. So based on this thing, price of the software varies uh, with very huge amount you can say. Then this is the example here. You can see that of circuit simulation. We are taking, these are the different parameters we are using here on right window, and these are this is MOS characteristic of transistor, and in this software we are using these number. So these parameters vary from one vendor to another. So a vendor who is providing more number of parameter for this simulation, they provide better solution. They are you can say competent in the market, and they give us industry standard solutions, but cost of those softwares are very high. And this is the analog simulation of that software only, and this simulation is basically you can see here there are three inputs. One is your A, B, C. This simulation is with the help of microwind software only. Here we are using microwind software, and ABC inputs are there, and this simulation is for full adder, and we have these two outputs, carry and sum. Here this is the spice simulation. As I told you that first we input our design using either schematic, and that schematic can be in the form of transistors, or it can be in the form of gates. So I just told you one step. There were three steps. One was you have to enter the schematic. Second one, you have to create Verilog file, and third one was you have to compile the Verilog file to create the actual layout of that particular chip. So this spice file is basically that V file. So this file is generated from the schematic, and this file gives you information about different components used in your design with their exact, you can say, physical size, with their exact connections. Here you can see that different connections are there, with their different sizes are there. So basically whenever we shift from schematic to Verilog file is not is nothing but it is your spice file, or sometimes we also call it as jet file, and that file gives you information about each and every device present in your circuit with its actual physical description. So this is the spice file, and we use this spice file and we compile it to get the layout. So when we talk about this circuit level simulation, there are some sources of errors in this circuit level simulation. Sometimes inaccuracies in MOS model parameters. Inaccuracies in MOS model parameters means if you have taken wrong values for different parameters, then your simulation may result in inaccurate result. Then the use of an inappropriate MOS model. MOS model here means what model you are using for this simulation, circuit simulation. Whether you are using level 1 simulation, you are using level 3 simulation, or you are using BSIM 4 simulation. If you are using level 1 simulation, it will be less accurate, but it will be very fast. Its result very fast. And if you are using level 3, it will be slow as compared to level 1, but it will be more accurate as compared to level 1. But if we are using BSIM 4, it will be accurate as compared to level 1 and level 3, but it will take more time for simulation as compared to your level 1 and level 3. And your source of error can be inaccuracies in parasitic capacitances and resistance. So these are different parameters which can create error in your design while you simulate it using different models, level 1, level 3 and BSIM 4. Then next thing is your timing simulation. Timing simulation is used to solve simple non-matrix calculations for checking your circuit behavior. The accuracy of such simulator is less than that of SPICE, no doubt. It will be less accurate as compared to your SPICE simulator, but it will be high in speed. You can say that execution time of this these type of simulations, it is almost 2 orders of the your SPICE simulation. So we can say that it is going to give you a rough idea about the timing of your complete design. We are not taking here any matrix calculation. It will be in the form of non-matrix calculation. It is going to give you rough idea about the timing, but it is not going to give you complete analysis of your design. Means it is not going to be accurate as compared to your SPICE simulation. Then next is your logic level simulation. Logic level simulation earlier. Now circuit level simulation means we are talking about actual physical size of each and every transistor. We are basically working on layout part. We are using layout, we are simulating it using different parameters, and our accuracy is going to depend upon the number of parameters we are using. Likewise, we can simulate our circuit using gates, and we calculate, sometimes we use these gates as unit delays, and we calculate the delay in the form of unit delay, like 1 delay, 2 delay, and we calculate overall delay of the circuit. These type of simulators can be highly optimized for your execution time. Means for example, if we work, as I told you, there are in case of backend VLSI design, you have 2 softwares. One is your DSCH, another one is a Microvent. In DSCH, you have the option, either you can create your design using gates, logic gates, and it also depends upon the circuit input. Means whatever circuit you have with you, whether it is in the form of gates or it is in the form of transistors. If you have the circuit in the form of gates, then you can opt for this logic level simulation. You are going to design your circuit with the help of these gates, then you are going to simulate your circuit in that logic form, and that is possible with the help of your DSCH software. So here also all logic gates are rarely active simultaneously. So logic events may be scheduled on a key. It means that your circuit can be evaluated on event driven basis. Basically, if you have one complete circuit, as I told you, your circuit complete circuit is not going to be active at a time. So you can partition your circuit depending upon the activity of your circuit, and each and every partition can work depending upon your event, and that event can be generated with the help of your clock. You can say that best example is your sequential circuits. This is the example. Here you can see that this circuit is developed with the help of your DSCH software. By using DSCH, we have created this full ladder by using different logic gates, and this circuit has been simulated in DSCH only, and this is the simulated output waveform of that circuit. So here you can just view, and these type of simulators you can give you fast idea about the functionality of your program. So from here you can easily check whether your circuit is working as per your requirement or not. all of us are well aware about this working of this full ladder. So once your full ladder is designed with the help of these logic gates, you can easily verify your truth table from these waveforms. So this is first step. We create our schematic. We create our schematic with the help of DSCH software. Then we simulate that schematic in DSCH only, and we check the behavior of our circuit, and we compare with it with our truth table. Next is switch level simulation. Switch level simulation here, as we all know that transistors can be modeled as switches. So it may be possible that the design available with you is in the form of transistors. It is not in the form of gates. So your software, it should provide you the option of capturing the circuit in the form of transistors. So if you can capture your design in the form, if it is available in the form of transistors, then you should have this option, and you are going to design your circuit. That thing is also you can do with the help of your DSCH. You can create your circuit with the help of transistors. You can make connection between them, and then you can simulate that switch level circuit using that DSCH. RSIM is the example of this switch level simulator. CMOS gates are modeled either they can be pull up or pull down structures, where RSIM dynamically calculates its rise and fall times. So example of this one is here. You can see that now the earlier example was for full ladder, and that full ladder was designed with the help of gates. Now here you can see that this is the example of what? This is the example of your inverter, and here this inverter is designed with the help of two transistors. Here you can see that this is your PMOS, this is your NMOS. So here we are using one input switch, and here we are using one LED to check the connection. This is connected with ground, this is connected with VDD. Whenever this input is zero means your PMOS will be closed, it will work as 1, and your LED will be high. And when it is 1, then your PMOS, it will act as open, and your this NMOS, it will be closed, and your output will be 0. So your LED will be 1 if your input is 0, and when your input is 1, then your LED will be off. So this is the circuit for your inverter. From here now you can easily just verify this circuit again, and here you can see that this is your input 1, it is high. Here it is input 1 is high, then your output is what? It is low. In case of inverter 2, your input is low, and this one it is low, and we are getting here high. In this way you can create your circuit at switch level, and then you can simulate your circuit in this form, and that is also possible with the help of your DSCH. Next kind of simulation is your mixed mode simulators. Mixed mode simulators, sometimes it may be there in your papers. Whenever you are going to search for different papers, you may get some circuits in the form of logic gates, and you can say combination of logic gates and your transistors. So in that case, we can combine both your logic design and switch level design. We can combine them. We can create our design by using gates wherever gates are required, and we can use transistors wherever transistors are required. We can make connection between them, and once your circuit is complete, then we can simulate our circuit in this mixed mode simulation mode. Means our software should be capable of providing us the ability to input our design either using gates and transistors, and then we should be able to view its simulation. Example of this, there are some circuits may be simulated using logic level simulators, and some may be simulated using circuit level simulators. So this facility is also available in your DSCH. We can create our own circuit either using gates or transistors, and then we can simulate it. So this is basically mixed mode simulators. Then timing verifiers. Here the delays through all the paths in the circuit are evaluated in pattern independent manner, and user is provided with the information about all these delays. User will get information about all the here we can say that for routing purpose different paths will be available, and the delay through each and every path will be communicated to the user. So user can opt any one out of these paths depending upon the requirement. CMOS verifiers work at the gate level or transistor level, and example of this one is your Perl program. Each transistor is examined and the direction of signal flow is calculated using circuit design methodology rules, electrical rules, and some supplied rules to the user. And the Perl program calculates RC delay at each node, and this is done by using RSIM simulator. Next thing is network isomorphism. Network isomorphism is basically nothing but you can say that it is the comparison between two networks. As I told you that whenever we go for our backend VLSI design, we start from schematic. So that schematic is created, either it can be with the help of gates, it can be with the help of transistors. So once the desired schematic is ready, the next part is we create its spice file or deck file, and then we take that deck file in our microwind software, we compile it, and then we generate the layout of that particular circuit. So now you have two circuits, or you can say you have two networks with you. One is your schematic, another one is your layout. Now your task or software task is to compare these two different networks. Whatever you can say devices present in schematic, whether all those devices are also present in the layout or not. Whatever connections are there in your schematic part, whether all those connections are also present in your schematic layout part or not. So basically you can say that it is the comparison between your schematic developed and layout generated, and these two are compared. Once they are similar, then we call them yes, there is network isomorphism between the two networks. So here you can see that an electrical network may be represented by a graph where the vertex of the graph are devices such as MOS transistors, bipolar transistor, diodes, resistors, and capacitors. Two electrical circuits are identical if graphs representing them are isomorphic, means each graph has the same number of devices, and for every device in one circuit there is matching device on the other circuit. Here we are talking about two circuits, one is your schematic, another one is your layout. So both circuits should be same. So device present in your schematic, it should also be present in your layout part. The matching devices have identical properties, means whatever size you have selected in for transistor, its width and length, its resistance value, then its connection with different terminals, it should be same in your layout part also. So that physical dimension is also very important. Each node in one circuit has matching node in other, means every node present in your schematic, it should be there in your layout part also. They have identical properties such as the same number of sources and drains attached to them and the same number of gates. So basically this is nothing but this is the comparison between two networks. One is schematic, another one is your layout part. It is basically used most often to prove that a layout is equivalent to a network extracted from a schematic or HDL netlist. So it is similar. So we also call this network isomorphism as netlist comparison. Another name is network isomorphism, or we can say it as LVS, that is your layout versus schematic. So this is the comparison between your schematic and layout, and both networks should be similar to each other. Only then we can say that a layout is exact, you can say, replica of your schematic. Then Layout extraction. Layout extraction basically it examines the interrelationship of mask layers. It means when you create layout, you have number of mask layers with you, and you have to check the interrelation between different mask layers. Means there are a number of mask layers, and one layer can be connected with some other layer. For example, layer 3 is connected with layer 7 with the help of some wire. So that thing, it has to be checked whether that connection is there or not. So it infers the existing of transistors and other components. They are related to basically design rule. So design rule checks, they check each and everything. They check for connectivity, whether all the connections are well in place, and they check for different you can say conductor widths. They check for size of transistors in terms of source, drain, gate. So commonly parasitic capacitances and resistances are reported in addition to transistor connectivity. So these type of things are reported in your these design rule checkers. Algorithms commonly used, they have different geometric shape to recognize active devices. So different algorithms with different geometric shapes are there. So you can recognize different devices. So you can see that in your that layout you have different layers with different colors. So each and every color has some significance. So for example, if you want to denote a PMOS transistor, it will have some defined color for it. You have to define some color. If you have NMOS, then you have to define some other color. And blue basically we are using for metallization, red color we are using for polysilicon. So each and every layer basically we define, and we define it with specific color so that it can be easily distinguished from other mask layers. This is now here you can see that this is the layout, and here the blue color means metallization, and this red color, this is for your you can say polysilicon gate, and this one is your PMOS, here NMOS. So different color has different meaning, and they are used to distinguish one layer from another in case of your complete chip layout. So once your layout is created, next important step is you have to check the DRC. DRC is basically your design rule check. If and the DRCs play a very important role when you two things are there. Either you can create your layout uh, in automatic fashion, means you can generate your layout, but still in that case also you have to check the DRC. But in case you are working straight away on layout part, you are creating your own you can say a layout. In that case, this DRC plays very important role. We check for each and every rule. If anything is not going well, if any error is there, then it is going to notify that error, and before further processing, we have to first eliminate the error. So if mask is completely manual, it is necessary to verify that the layout conforms to the geometric design rules. And this is normally achieved by using what? By using your design rule checkers. So design rule checkers are there to find out this thing. Next is your pattern generation. Once your different marks are available with you, and this pattern generation is basically is the last step in design process. It is the operation of creating the data that is used for your mask making. A common format for pattern generation is electronic beam exposure system, EBES. Normally we use this system to create different mask layers, different mask, p-type mask, n-type mask, polysilicon mask, metal mask, different metal layer mask. So all these masks are created with the help of this EBES system. Once all these masks are available, then we can use these masks. We use these masks on silicon area, we drop the impurities, and then we come up with our chip design. So basically these are different steps in our complete chip design, or you can say these are the different options, and these options depends upon different CAD tools, and you should have good knowledge about the CAD tools, what CAD tool is available with you, and by using this CAD tool what kind of circuits you can design. So it is very important from designer point of view. Now finally I conclude this session. So we can say that depending upon the circuit with this designer, so before start of any design you should have circuit of that design, and that circuit will be either in the form of transistors, it may be in the form of gates, or it may be in the form of you can say HDL language, VHDL or Verilog. Designer will take that software and it will check the availability of tool with him or her. So whether your tools support HDL, whether your tools support transistor level capture, whether your tools support logic level capture, if it is there, then you can proceed further. So designer can capture, designer can verify, designer can synthesize this circuit using these suitable options available in the software. So you should have very good idea about the software. Once this idea is there with you, means what are the options available in the software, then circuit designing, whether it is front end VLSI design or it is back end VLSI design, it is not tough task. So only thing you should have good idea about these CAD tools, then you can proceed with your circuits, design of circuits, and later on you can add on research part in those circuits. So finally, references for this whole session are you can go for this Neil Veste's book by that is CMOS VLSI Design, second edition. You will get all these different tools, categories, capture, verification, and synthesis. Then you can have a user manual for this Xilinx ISE. Xilinx ISE quick guide is there, and then its reference manual is also there. You can refer those two references, and then user manual for your DSCH and microvent. And these are the references used for this session. And with this, I just close my session here. So thank you very much. And now I invite queries from your end. So if you have any query, please go ahead with your query part.